Greetings. Today I wanted to talk about memoization. To illustrate the benefits of memoization, I would like to share with you the traditional recursive definition of Fibonacci. Given an input n, we recursively compute the preceding two terms until we reach our base cases, the 0th and first terms, defined here as 1. Note, you can also define the 0th term to be 0, which shifts the index I've used here by 1. The problem with this approach is that for each function call, we must always compute the result backwards from our base cases, repeating many and many computations to get the result. This approach gives us a time complexity of O of n squared. And this is where memoization can save much time and computation. Here I have created a generic function to memoize another function. Note that this function returns a function. So, given a function that expects a given input type and returns a given output type, we create a cache. We then use this cache to store and look up already computed results to that function. This returned function takes an argument of the input type, attempts to look up the result from the cache, or, if it does not exist in the cache, applies the argument to the given function, stores the result in the cache, and returns the result. Note, I have included the cache.synchronized to ensure thread safety, but this can be omitted if the application is single-threaded. We can then use this generic memoize function to define a memoized version of Fibonacci. In Scala, we can define values to be functions. In this context, I have defined fib to be a function that takes an integer as an argument and returns a big int. For this purpose, the lazy keyword is not particularly important. It just means that it isn't computed till it's needed. This function is the result of memoize and utilizes a partial function as the argument. Instead of explicitly matching on the argument, as seen in the traditional Fibonacci, we can remove the boilerplate using this syntactic sugar. Finally, note that this definition is still recursive. However, each call to fib is a call to the resulting function from memoize, meaning that the cache is checked before the inner function is called. In this way, we can consider the time complexity for this function to be linear, or O of n. To show you some trivial examples, I created two utility functions to time and pretty print some examples. Here they are. I won't go into too much detail, but you can pause if you'd like to check them out. Here's a small runner I made to illustrate some of the stark contrasts between the two methods. First, we compute the time taken for both functions using 41 as the argument. This was the largest argument, which took under 2 seconds for the traditional Fibonacci to run on my machine. Then we repeat this using the same argument, 41. Finally, we compute the 1000th term using the memoized version of Fibonacci. So, computed piecewise, this function could handle terms much larger, but 1000 stack frames is the maximum in one call. So what can we see from the results? Traditional Fibonacci takes roughly the same amount of time for the first and repeated test. Memoized Fibonacci takes 1 millisecond the first time and 0 milliseconds the second time, as the result had already been computed, and thus was a simple lookup from the cache. As you can see, this significantly reduces the time taken. For the 1000th term, we achieve this using the fib function in only 6 milliseconds. As you might be able to see, hopefully, memoization can be very simple, and given a use case where repeated computations can prove very expensive, saving those results can offer an enormous efficiency boost to a system. If you have any questions, requests, or constructive suggestions, feel free to leave a comment. Thanks for watching. 1,000 carats out.